All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute yourself and ask those questions. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. So no classified discussion is allowed. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Let me introduce our speaker today. It is an honor to host Yexiang Su, who is an assistant professor at Purdue University. The goal of Dr. Su's research is to bridge large-scale constraint-based reasoning and optimization with state-of-the-art machine learning technique in order to enable intelligent agents to make optimal decisions in high-dimensional and uncertain real-world applications. More specifically, Dr. Su's research focuses on scalable and accurate probabilistic reasoning techniques, statistical modeling of data, and robust decision-making under uncertainty. Recently, Dr. Su has been developing hybrid reasoning and learning approaches in the emerging area of AI-driven scientific discovery. Today, Dr. Su will present an exciting topic, which is scaling up AI-driven scientific discovery. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Dr. Su by asking one random question. Since today is Friday, in order to recommend a movie for the weekend, what is your favorite movie?
What is my favorite movie?
Yeah.
Shawshank's Redemption.
Oh yeah, I have watched that. Yeah, that's very inspiring movie. Okay, stage is yours.
All right, thank you for the introduction, Yongsu, and sorry for this very long title. Today I'm mostly going to talk about scaling up AI-driven scientific discovery. And I am Yexiang from the Department of Computer Science at Purdue. So we are in Indiana. And this is work with Nassim, Nan, Chonghao, and Professor Xinhang Zhang and enter Azab from Purdue. So let me start by motivating AI-driven scientific discovery. So over the years, there's tremendous progress in scientific the scientific discovery field, and especially with large-scale simulations that given a physics model, these large-scale simulations is able to predict what will happen for these large-scale physics models, and that can be compelled. Somehow it's okay. So that is can be compelled with experimental observations, and the physicist can see how well the match between large-scale simulation and experiments is, and if there is not a good match, then they will go back to the the physics models and try to update the model and do the simulation again and see and to improve the match. And this overall leads to a scientific discovery loop that you loop in between models and simulations and experiments to discover new knowledge. This talk is mainly going to be using artificial intelligence to automate this process. And we asked the question, can machine learning be used to automatically discover new science? We will talk about an end-to-end framework for AI-driven scientific discovery, integrating pattern recognition with physics simulation. We'll also talk about how we scale up this AI-driven scientific discovery framework. So our approach was motivated by the real-world applications of AI-driven material discovery in extreme conditions. So for this application, we would like to search for strong materials under heavy irradiation and extreme high temperature. And we would like to understand the defect formation, migration in these extreme conditions. And this is, of course, meaningful to discover new materials for future nuclear reactors. So the kind of data that we work on are these in situ experimental data, and we are collaborating with scientists from the Argonne National Lab, which is on in the other side of the country. That they have this in situ experimental setup that basically is a electric microscope, and you load your material sample here. And then the material sample is being, baked, so raised to a high temperature, and at the same time, bombarded by ion irradiations. So under the electric microscope, you can actually see, the microstructure of these. So in this case, this is a copper under nanoscale. And so there are certain, defect clusters of this in this copper material. And if you look at this, look at these nanoclusters under electric microscope, you see that over time, under this high temperature and irradiation, these void clusters, they actually change in their related relative positions and size. So the question we would like to ask is, can you use a set of partial differential equations to describe, the movement of these nano clusters? And that, is meaningful for material scientists in understand the underlying theory behind this high temperature and irradiation bombardment and come up with new materials. So here is a in situ video of these the real in situ video of this copper material under 350 degrees C and current ion irradiation. Now, if you focus on some of the small voids, so if you look at this one and these small voids, you see that they indeed are moving, and they are following some random moves. And our goal is to learn these physics models that can explain their movement. Now, I really want to say that novel artificial intelligence enabled techniques are needed to analyze these large-scale data. So in situ experiments provides terabytes of the data. In fact, a 10-minute video of this electric microscope videos, they would provide data at a scale of terabytes, and it will cost 3.75 months work for a full-time PhD student to annotate and analyze these videos frame by frame, even if he is working very fast. He spent 5 minutes annotating per frame. So that actually, really motivated our research. Today, I'm going to talk about physics knowledge discovery via neural differential equation embedding, efficient learning of sparse and decomposable PDEs using random projection, and rapid symbolic regression using scientific approaches, which are some recent work that we have been doing. As I have said, the task that we are trying to do is we have these in situ videos of nano voids that they change in size and move in related positions. And we have some annotations every few frames. The task we are trying to do first is, physicists, the experimentalists really want us to track the position and the movement of these nanovoids. At the same time, we would like to learn, the parameters of a set of physics models that can, predict the evolvement of these nanovoids. So this is actually from our learned model, and you can see to predict, what is going to happen for these nanovoids, and you can see that its spatial and temporal movements are actually close to the original video. And we have a learned explicit physics model for that. How are we going to do this? Well, we are motivated by the scientific discovery process of physicists. So as we have just talked about, physicists, they actually go through this scientific discovery loop by integrating simulation and updating their models and trying to update their models repeatedly to match experiment observations with the simulations. So what we are doing here, our work is really to replicate what the scientists are doing, however, with artificial intelligence. In particular, what we are doing is we have these in situ video frames, and in the first step, we have a recognition neural net. This is a we use neural nets that is inspired from computer vision, and these neural nets, we try to use these neural nets to extract the values of the partial differential equation variable values from these in situ video frames at two different timestamps. Then, we have this second neural net, which is this neural differential equation net that takes the states of these partial differential equation variables and try to predict what will happen for this dynamic system at a later timestamp. And also we have annotations. So suppose the recognition net and the neural differential equation net, they are both trained, then which means the recognition net is able to extract the values of these partial differential equations from the in situ video data, and the neural differential equation net is able to simulate, and it has the correct parameters, and is able to predict, correctly what the future is. Then the simulated results, the recognized results at a later timestamp, and the annotations, these three outcomes, they should match. Now, of course, in the beginning, when you, initialize randomly the recognition net and the neural differential equation net, randomly, then, this is not going to tell you, what are the states of these PDE variables, and the neural differential equation net is not able to, readily predict into the future. Therefore these three outcomes, they won't match. What we do is we impose a loss function that actually penalizes the difference between the annotation, the simulation, and the recognitions, and we use back propagation to update both neural nets. Our hypothesis is when the training converges and the three outcomes, they match, the recognition net is able to extract the values of the PDE equations automatically from these computer vision data, and the neural differential equation net is able to learn the correct parameters of these partial differential equations. at the time we developed this work, we independently identify that this neural differential equation net can be formulated as a convolutional neural net. But later on we realized that other people have made similar discoveries as us during the same period of time, and really we see there is a rich literature that actually are all about learning physics models from partial differential equation trajectories from the data, and including many scientists probably here in the audience. And our work is, we integrate, pattern recognition, computer vision with neural partial differential equation net, and we would like to discover these the states of the physics systems automatically from the vision data without so most of these models need the trajectories of PDEs given to them. We want to integrate computer vision together with neural partial differential equation net. So if you look at our results, we have this TEM video. So this as the input and some annotations, and we compare our model with a black box neural network approach. So first, in terms of tracking, so here the red parts are denote the tracked results for these nanovoids. In terms of tracking, both results are doing quite good. So the neural nets is also able to provide reliable tracking with very high accuracy. However, what makes it interesting is in terms of predicting into the future. So this is the result. So if you give a TEM image as a starting point, and then you ask the neural net to predict what is going to happen into the future, how is this nanovoid going to change over time without embedding a physics model. So what you see is the prediction quickly becomes non-physical. So this is some predictions that is cannot be the case in real materials. But then we said, this may be, too difficult for the neural net because it simultaneously needs to predict the future and at the same time extract the values of these partial differential equations. So how about we actually feed the neural nets with the ground truth values of the partial differential equations and ask the neural net to predict the future. And this is, in terms of the states of the partial differential equation variables. So this is its prediction. As you can see that it is still not able to, reliably predict into the future. Our approach, because we actually embed these phase field models for this nanovoid evolvement, and we are able to reliably predict the future, and in fact these matches with the regional dynamics quite well. So we also deployed our model in the analysis of real-world in-situ video data, and so this is the real-world data, so it's a lot more noisy, and we can provide reliable tracking with high accuracy. We do have these, sometimes these show up not perfectly well, but overall the accuracy is good. We also show that our model can predict the evolvement of a new physics system that is not used during training. So it works well generalizing to new initial conditions. So So this is the first part of the talk that I presented a framework for physics knowledge discovery using neural differential equation embedding, and then the second part of the talk that is we are going to ask the question, how we can scale up AI-driven scientific discovery, and in this case we explore efficient learning of sparse and decomposable PDEs using random projection. Identifying PDEs automatically from data has attracted great research interests. However, this is very expensive. Scientific simulation is already highly expensive operations, and the computations can take days or even weeks because it actually involves handling billions of mutually interacting elements. Now, the backward learning, the idea that I have just presented, is even more expensive because you actually need to embed this forward simulation into the back propagation process, and that results in a even more expensive framework. So the question we are asking is, how can we expedite both forward simulation and backward learning? And our answer is if we can take advantages of the problem structure. So here, the problem structure that we are looking at are really inspired by the physics problem that we are dealing with. So this is the nanovoid evolvement, and this is the grain boundary change, the grain growth for materials. And all these problems, they have a very nice property that they are interfacial problems, meaning all the interesting phenomena that you actually see are actually in the boundaries of this system. So if you look at nanovoid, the changes are really at the boundary of these nanovoids, and similarly, the changes are along the boundaries of these these multi-grain material systems. So not only the changes are concentrated on the edge of these systems, if you write out the partial differential equations that describe the change, the partial differential equations are actually easily decomposed into the linear combination of learning parameters times a set of sparse features. So here, the red, the parameters with the red underline are the parameters to learn from the data, and the terms in blue are the features. So you see that not only the changes are sparse, the features are also sparse. Okay. Now this is also true for other variables in this system, and it's also true for grain growth. So now, if you have this very sparse physics system, what you immediately realize is you are dealing with so this is the loss function of the learning problem that you are trying to learn, that basically you try to minimize the loss. The loss actually penalizes the difference between the observed update of the system and the predicted updates from your current model. Now, if the observed update is highly sparse, and the features are also highly sparse, then if you look at this loss function, it is actually a gigantic sum with many elements, but most of the elements they do not have, in most of the places they don't have any updates, and all the features are also zero. So most of these loss terms are zero terms. So you are actually dealing with a loss function that in a lot of places you don't actually need to worry about the change. Now, how can we, one caveat is, if you know where the loss is going to be zero, right? If you know that beforehand, then you can carry out, this learning in those places, in those areas that only has non-zero losses, and you can greatly reduce your computational overhead. However, the problem is you actually don't know these terms. So these terms, any term can be non-zero over learning. You just know that, overall there is a small fraction of the terms that is non-zero in this loss function. So what you can do is, we use this random projection. The idea is to, change the loss function a little bit. So let's say you have this the loss, and we multiply this loss with a random projection vector, and in this case are the vectors of zeros and ones. Now in practice you are not restricted to use a projecting vector of zeros and ones. You can actually use different other projection vectors, but we just use these zeros and ones as a illustrating point. So what will this this projection vector of zeros and ones actually do to your loss vector? Well, it basically extracts a few terms, which are the terms in which you have these ones at these corresponding locations, and you sum them up, right? So basically, if you project this vector using these random 0, 1 vectors, it is actually, group a few of these loss terms together and then square sum them, okay? Now, this is actually, you see that, it's not that ideal because you are changing the loss function. You are, combining many terms together and square sum them instead of square sum them individually and add them up. However, the thing is, the caveat you realize is because most of these terms are zero. Now, even if you combine several terms together, it is unlikely that more than two or two or more than two non-zero terms will be grouped together. Okay, so you are changing. So essentially, if you look at you are changing the loss function by grouping these terms, terms together using these random, projection matrices. But you are not changing the loss function too much, meaning that it's highly unlikely that you get many non-zero terms that is being grouped together. So in fact, we have this, theorem that is able to, quantify, what is the difference by doing these projections with these random vectors, and we can see that, the loss function, it actually brings you a constant approximation to the original loss function, which means during learning, if you minimize your new loss function, which is this surrogate, if you find an optimality that minimizes this loss function, at most you will also find a good solution to if you're minimizing the original highly expensive loss functions. So because of that, we developed this new idea that's based on random projections. We first, random project both the the features and the spatial and temporal changes into this compressed space, and then we carry out the learning, entirely in the compress the space without ever project them back in the original space. I want to say that in our approach, the compression is done as a pre-processing step. So even though it is, the compressing is a costly step, but it's only done once. So the overall, computational overhead bringing by the random projections are not that much. In terms of the experiments, we are able to see that, our model still learns, still has reasonable learning performance, even after the dimensionality has been projected to 0.05% of the original size. So if you look at, this row, this is basically nanovoid evolution. If you have the data compressed to 0.05% of the original size, still the learned model is able to simulate similar dynamics at the as the original the model learned without compression. Sir, I don't know if we allowed to ask questions during the talk, or we will save the questions to the end.
Well, yeah, okay. So we can pause and then we can take some questions. Actually, in the chat room, there are some.
Oh, there are. Okay, I don't know how to open the chat room. So.
Well, actually, Pat and Daniel was posing some questions. Do you guys want to unmute yourself and ask that?
Yeah, Daniel should go first.
Daniel, are you there? I guess he's not here.
Well,
Pat, you can go.
we can read it. So Daniel's question is, the nanovoids seem to have high contrast against the background. Have you tried any mathematical operations to track them instead of statistical learning? Now, I didn't quite understand that, but I interpreted it as, if you could identify these nanovoids, then you could describe them as points and radius or something, and you could describe, why not describe them as ODEs rather than PDEs?
Yes, so that's a very good question. So now, did we try use tracking algorithms for these nanovoids? Yes, we did. But what we are more interested is in the physics behind the nanovoid. So that is, the whole point of, we want to use a set of partial differential equations to describe that. So in terms of whether you can actually use...
Did you just say that ODEs are not physics?
No, I said we used tracking algorithms from computer vision to track these nanovoids.
Oh, yes, but if you could do that, then you could describe the nanovoids as objects, and you could as particles, and you could use ODE models rather than PDE models to describe their behavior, and that would be much simpler. And so it's a question of how you formulate the problem.
Yes.
Could you have formulated the problem that way? It would clearly be computationally much more tractable. And so that's what I would like to know. I think that Daniel may have been heading in that direction, but he didn't. But he may have meant something different.
Very good question. So I think we can formulate the nanovoid evolution using ODEs by basically, looking at, the changes of their diameters and assume this is a perfect sphere, and they are being and the change of the diameters of this sphere and so on, and extract this using a few parameters like the radius, the x and y and z locations, and turn that into an ODE problem to process it. So that is that I believe is doable, and it will be a good, it will be a good, a good model that actually, share a lot of light to certain degrees of this physics system. Now, but what makes it more interesting is we actually observe. So if you think about it, why the nanovoids actually move in the spatial and temporal domain is actually because the rate of shrinking of the nanovoids in different part of the nanovoids, they are different, and therefore the difference of the rate actually causes the nanovoids to move. And we also observed empirically that it's not always sphere, and they are and in some materials, the shape of the nanovoids, they are in some physics systems that we are working on, they have elongated nanovoids. And so on. That's the shape is way more complex.
So it sounds
In
like
that
you're saying that physically it's better to view this as a fluid of some kind rather than as a set of particles, and that PDEs are more appropriate in that context. Is that where you're heading?
Yes, yes,
Okay,
and
that's
it
fine.
may it may give us more physics knowledge. It may
Okay.
give us.
So in the meantime, Ravi Abram has made some comments, and you may want to let him speak.
Yeah, Ravi, if you want to unmute and go ahead.
Just a thought on the loss functions, right? So I didn't see a Pareto on the loss functions. If some of them are dominant, then you can exclusively select them out. And the second question is, of course, everywhere you're tracking these objects in ODEs, as was mentioned, they could burst, right? So you're not looking at some equations where there are disruptions, like typical shock waves, right? So in this example, there are none. So it's just a simplified ODEs with different loss functions. But if they're not, then potentially the bubble could burst. So that your question is, if I have Paretoed like 5 or 6 of the loss functions to a higher degree over the rest, then you can almost predict faster. But at the same time, you should see if there are some disruptions that could happen.
If the disruption
so-
happens, then isn't PDE a better model than ODE?
And the question is, are there disruptions in those PDEs, like a shock wave suddenly appearing, right?
Yeah.
We never examined those things, but there could be possibilities like that. It's just a question of saying, okay, what's the probability that in the current situation right now, those four or five gaps will either coalesce or break apart?
Very good question. So the first part is do we have this random effect that sometimes the void burst and so on and so forth. That is very good. Indeed, in experiments, in experimental data, we see these kind of things happening. We see this kind of things happening. Okay, and currently the model is the models. The theoretic physicists, they come up is they use some kind of random effect to capture this, and our learning systems are not fully capturing that. But that is indeed very exciting. That we want to look into that. As future work. And Ravi, what is your other question?
The other question is, if you look at your loss function, you're telling there's a large sparseness between the ones and zeros all over the place. There's still a large data set, right? So
Yes.
you also mentioned not introducing ones and zeros, but let's say some fractions, for example, some weighted fractions. If you really look at how those Pareto on those larger groups are, so imagine there are blue bubbles versus yellow bubbles. I'm just throwing out this, right? So they're on the interface sites. So you're looking at something saying, okay, the nature of the initial conditions are all blue. So the more likely that the blues remain, right? And that basically means you're not looking at just the large vector of weighted on ones and zeros, but only a small cluster weighted on it. So then the learning curves that you're trying to optimize on will become smaller and smaller, right? So you can be faster. That's what I'm saying.
Yeah, I didn't quite grasp your idea. I think probably we let's put this offline. And I think you are talking about something exciting that currently through this tele communication, I am not fully grasping your idea, but I think that's our interesting ideas.
Yeah, let's put that discussion later or offline. Why don't you move on?
Okay, yeah.
Yes, yeah.
So the third part is about symbolic regression using scientific approaches. So for this part, this is some recent work that we have just been starting. Eventually, we would like to actually see this working out for learning partial differential equations, but we are starting on small examples of learning mathematical equations from this data. So the starting point is artificial intelligence has been progressing tremendously in scientific domains. But if you look at how scientists are doing are learning these scientific laws from data, they actually are very different from these neural network models in the sense that they often are able to learn these very elegant models from an incredible small set of surprising data, and the models, the learned models and the equations, they are highly elegant and they are interpretable, and their learning process is, believe or not, quite different from today's machine learning approach. That they actively form hypotheses and they actively explore the experimental space with the purpose. So these these different characteristics made me really think that can we is the current these neural networks based on stochastic gradient descent is able to give us new science. It may be able to refine our physics models. For example, this is the law of gravitativity. It may be refine certain parameters. Is this inverse to r squared or r to the 2.1 squared or so? But to what degree these can help us discover new physics laws? That is the question that I have been asking recently. So I believe the next stage that for learning scientific data from learning scientific models from the data really needs to be to have these reasoning powered learning approaches that we actively form hypotheses and design experiments and go through these closed loop of experimentation, hypothesis, and learning. And for this is just some starting point of our recent work that we would like to explore how control variable experiments as a classic scientific approach, whether these experiments can be used to expedite scientific machine learning. This is the symbolic regression task that basically you are given a data set. Okay, so here you have a data set of X and Y, and you try to learn a polynomial, a mathematical equation that maps from the x to the y's. So this is, of course, a good benchmark mimicking the scientific discovery process. We have been talking about learning partial differential equation models. This is a simplified version of that process. Now, this problem is also incredibly difficult because of the large search space of all the possible expressions. Some audience have seen this slide, but for the rest, if you haven't seen this slide, are you able to discover what is the mathematical equation that maps from the x to the y? Well, this is actually very difficult because I actually intentionally make this very difficult. But as you can see that this is a highly non-trivial problem that you are given a data set and you try to figure out what is the polynomial that maps the input to the output. But how about I ask you to only look into these rows and come up with an equation that maps from the input to the output.
X1 plus X3.
Yes. So I actually run these through many undergraduate students here. That they are able to figure this out. Okay, they are able to figure out if you just look at these rows, then x1 plus x3 is a equation that actually describes so 2.5 plus 9.5 is 12, and so on and so forth. Now, how about these rows? I actually asked the undergraduate students, and they are able to figure out that this minus x1 plus x3 is the equation that actually maps the input from the output. So if you look at minus 3 plus 4 is actually 1. Minus 4.2 plus 2.2 is minus 2, and so on and so forth. So if you have this, the red rows and the blue rows, you can actually, stare at these equations a little bit, and then you find out that in the red rows, the x2s are actually 1.0s in red. And the blue rows, the x2 are said to be minus 1.0s. And if you look at the coefficients between before x1, then in the red rows, these are the red 1.0s, and the blue rows, these are minus 1.0s. So by doing that, you should be able to guess, it is the equations x1 times x2 plus x3. And that is indeed the ground truth equation. So if you ponder through this process a little bit, then you will see that this process is really the process of doing control variable experiments. You first hold x2 to be 1.0, and then you find a simplified equation under these conditions, and then you host the x2 into minus 1.0s, and then you see another simplified equation, and you are able to figure out the equations by actually looking at the outcomes of these control variable experiments. And you can see that these control variable experiments greatly simplified symbolic regression. I see there are a lot of discussions. It's very quick on my screen, so I'm not able to follow these discussions.
Don't worry about it.
Nothing serious. It's just carry on.
Yeah.
Okay. All right. So let me first talk a little bit about what a control variable experiment is. This is indeed this is indeed one of the oldest ideas in scientific discovery. So it is a classic procedure widely implemented and proven useful in science. In control variable experiments, you have certain variables controlled, meaning that in one trial they are held at a single values, and then you study the relationship between the dependence variables and independent variables with this set of variables controlled. You also have these free variables, which they allow to change in values within one trial. We assume that there is an underlying expression that generates experimental data. So this is a reasonable assumption if you try to do this symbolic regression task. When you are working on control variable experimental data, because you have certain variables that is held as constant, then what it appeals to you is actually the equations are actually coming from a reduced form equation that the corresponding these controlled variables are replaced by the constants. So as a first step, we recently explored this idea of control variable genetic programming that we first we try to learn these symbolic equations from control variable experiments. In the first step, we actually hold most of the variables except for one as constants, and we try to use genetic programming to actually learn an equation that links the output from the input. So because we are only starting the dependence between the output and one input, it is relatively easy. So in most cases, the genetic programming algorithm is able to discover the correct reduced form equation. Then what we do is, in the second step, we let one variable to vary, and now we study the relationship between this output variable and two independent variables. In this case, we ask genetic programming to extend from the first step. What is the new equation that involves these two variables that can best explain this data. And then we carry on in the third step and fourth step. Finally, we let all the variables to vary, and we learn an symbolic equation that maps the output from all the inputs. And experimental results actually show that our approach is able to outperform a series of approaches based on different ideas, based on genetic programming, risk-seeking, reinforcement learning, and more and more. Let me say that I actually discovered this, and we are very excited about this, and we actually later on, and when we actually present this as in one of the other venues, and we discovered that one of the pioneers he actually is in the audience today. He actually pioneered this approach many years, in fact, like 30 years ago. Of this approach, but I believe this is the correct way of doing science, and this exciting idea has been forgotten in some after these many years, and instead of focusing on building more and more sophisticated, complicated neural networks, I think this old idea of based on how we do science can shine, in today's, with the development of these complicated and, fancy neural networks with more computing power and so on. And this is also, this is only a first step that we look at this very limited problem of equation discovery, symbolic discovery, and we will, certainly push this to, more complex scientific phenomena. Now, let me talk a little bit about, some efforts that we want to see if this kind of ideas can be, applied more broadly in learning partial differential equations. So here is a phase field model that's actually, if you simulate this phase field model, it actually generates, it grows a snowflake out of these phase field models. Now the question, you can use, the learning approaches that we presented before to actually try to learn this phase field model that determine this process. It is actually very difficult because this function is highly nonlinear. What we do is we try to set up these controlled learning experiments that we first generate data in which the blue parameters, they don't matter in predicting the future for those kind of data. And in this case, the model can focus on learning the red parameters alone. And then after we, the learning converge on the red parameters converges, and they are, they converges. We let, we generate new data that allow the model to learn the blue parameters. Now, if you look at the experimental results, so this is the ground truth that actually you grow, it's a snowflake. But if you learn all the parameters at once, this is what you get. Basically, you get these snowflakes that, it is still a dendritic solidification process, but the number of petals of this snowflake is actually wrong. Okay, so it's a different shape. But if you follow, this customized, control variable learning experiments, that you are able to, learn this snowflake that is, exactly like, the ground truth. So this is the last slide. In summary, I talked about data-driven scientific discovery, learning PDE models from the experimental data, integrate deep recognition networks with neural PDE net. And I talked a little bit about, using random projection to improve efficiency, and, use scientific approaches based on control variable experiments to expedite equation discovery. And we deployed our methods in searching for, in learning the nano-structure evolution for materials under extreme conditions. And there are, of course, a lot of future works in terms of extending to non-sparse PDE updates, active scientific discoveries, and so on. So I see there are a lot of discussions. I'm not able to follow them because it's literally it's on my screen. There's there's 1 second and then they disappear. So
it's okay. I was giving people references to some of the older work, but also someone raised the issue of applying this last part of your work to handle missing variables, things that are not observed but that are still, say, having a causal influence on the system. And I mentioned some early work we did, but I agree that's a really important issue. And if you have any thoughts on that, maybe you can tell us. Yeah,
that's identifying missing values, that would be amazing. It's kind of like, you will have to identify that there are the predictions are deviating from the experiments. in a it is not caused by random noise. There is, in a systematic way, the experiments are deviating from the experiments are deviating from what the model predicts, and that involves how you can identify that there is a systematic mechanism that it's a systematic deviation, and that, I think, yes, indeed, it's probably can benefit from causal inference and other approaches. I don't have a good answer for now, but that is very important and a very important question, and needs more future work.
Sounds good. Well, any other exciting discussions we need to do? You can unmute yourself and freely.
Not me, but we should follow later. I'm sorry I haven't followed up after the symposium, but I'm excited about this work, and I'd love to collaborate.
Pat,
Yes, Pat. Yes, we should follow up. Yes.
Okay.
Well, given the interest of the old work, Pat, maybe you want to give the second DDPS seminar.
Sure, it would be interesting to. Well, actually, if you go back to the recording of the first seminar I gave, I actually did review.
Oh,
but I could. We can explore that for sure.
Yeah.
And then Zheng can come and he can give me trouble during my talk.
Yeah.
Okay. Thank you.
All right. Any other question from audience? You can unmute yourself and.
This is very interesting. I've gone out of academia for a very long time. I'm in the professional supply chain business, so it was real fun. Thank you.
Awesome. Anyone else? Looks like not. Well, let's thank our speaker, Yexiang, for the wonderful talk. And given the situations, he has to go to the airport to catch the plane in an hour now. He was gracious to still make the talk today. Thank you so much for that.
Well, thank you, Yang-Song, for hosting me. Thanks a lot.
All right, sounds good. Hopefully after this talk, a lot of collaboration is going to be introduced between you and Lawrence Livermore, or even other external folks.
Yeah.
Thank you, Yexiang. Let me stop the recording.